welcome to my channel. Today we will solve the problem left slash right side of right side view of a binary tree. Let's first understand what is the meaning of left and right side view. So suppose this is our binary tree 1, 2, 3, 4, 5, 6, 7. So what will be the right side view of this tree? If we view at this tree from the right side, then what are the nodes which we can see? We can see 1, we can see 3, and we can see 7. So 1, 3, 7 is the output for the right side view. What do we see the the tree from the left side? We can see the node 1, we can see node 2, we can see node 4. So 1, 2, and 4. This is the output for the left side view of a binary tree. So now we will solve this problem for the right side view and later on draw the intuition from the left side view. Okay, the solution will be mostly similar with some minor changes. So we will discuss the right side view in full detail, complete detail, and after that we will discuss the left side view briefly. Okay, so this was one example. Hope it was clear. Now we'll move on to some other example, which will give us some corner cases. Suppose this is our tree. Yeah, suppose this is our tree. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So, what can we see from the right side? We can see the nodes 1, right? Then we will see from here, if we see 2 will get hidden behind the node 3, right? So we will see 3. Now from here, if we see this nodes 4 and 6 will be hidden behind 5. So we'll see node 5. Now we come down here, this node 7 will be hidden behind node 8, right? So we can see node 8 at this level. Then again we come down, we can see node number 10 because 9 will be hidden. So we can see 10, and then again finally at the last level we can see node 11. So this will be our output. This is the right side view for this binary tree. So how to come up with this solution? So what you can observe here is at each level, this is level 0, and let me change the color. This is level 1, this is level 2, this is level 3, this is level 4, and this is level 5, right? So at each level we are visiting only one node, right? Not visiting, I mean only one node will be the rightmost node at each level. So at level 0, the rightmost is 1. At level 1, the rightmost is 3. At level 2, the rightmost is 5. So at each level, there is exactly one rightmost node, right? Which we have to find out. So how will we find the rightmost node? So at each, we will do a depth first search traversal of the binary tree, and at each level what we will do is we will first traverse through the right subtree for each node. So for level 0, first we will see if level 0 we have the rightmost node or not. We do not have, and this is the rightmost node. We will store it. We'll come to the right again. Here for level 1 we will see if we do not, if we have the rightmost node or not. We'll see we do not have it, so we'll store this. So this will also get stored. This is also stored. Now at level 2, we'll say if we have a rightmost node already stored or not. We have not stored it, so we'll store 5, right? Now if we come down to right, this is a null, this is null, this is not a valid node. So we will backtrack to the node 5. Now we will visit node left node for this left child of this node. So left is also null, right? This is null, so we will backtrack. Co- Now we have visited both the left and right subtrees of this node. So again we'll backtrack. We had visited the right child already. Now we'll visit the left child. So left child at level 2. We will see, have we visited the rightmost node already? Yes, we have visited, right? This is in level 0, this is 1, this is 2, this is 3, 4, 5. We already visited 5, so we'll not store this. Now we'll come to the right child of this node, which is basically null. So this is not valid. We'll backtrack. We'll come to the left child of this node, which is 8, which is at level 3. So at level 3, we will see if we have visited any node. No, right? So we will visit this node 8. Now we'll come down. We'll go to the right child of this node 8. We'll see at level 4, have we visited any node? No, not yet. So we'll visit this. We'll visit 10. We'll backtrack. We'll try to visit the left child of this node 8, which is a null. So again we'll backtrack. We have already visited both the right and left child of node 8. We'll backtrack. 4 is also visited, 3 is also visited. We'll backtrack to 1. Now we will visit the left child of 1. Left child of 1 is 2. So we will see at level 1, have we visited the rightmost node? Yes, at level 1 we have already visited 3. So we will not store it. We'll come to right child of this is which is null. Again we'll backtrack. We'll go to left child. At level 2 we will see, have we visited any node? Rightmost node? We have visited already. So we'll not store this. We'll come down. We'll come to the right child first, which is null. Again, then backtrack, come down to level 3. At level 3, we'll see, have we visited the node? Yes, we already visited 8 here. So we'll not visit 7. We'll not store 7 basically in our output vector. And then we'll come to the right child, which is null. We'll backtrack. We'll go to the left node, left child. And at level 4, we'll see, have we visited any node? Yes, we have visited 10 already. So we will not visit 9 here. We'll go to the right child, which is null. So we'll backtrack. We'll go to the left child. We'll see that at level 5, have we visited any node? Not yet. So we'll store 11 in our output. So at each level, there is exactly one rightmost node which we have to visit. And once that is visited, we will not visit any node on that particular level. So for this, what we have to do is we have to do depth first search traversal. Okay. And first we have to first we have to visit the right child of each node, and then we have to visit the left child of each node. So this is the s- intuition. So now let's code this. Let's write down the code for this problem. So let's again go through the problem statement and the example given here. So as I said, the right view is for this binary tree is 134. That's what is printed here in the output. Okay. And let's see what are the constants. The number of nodes in the tree is in the range 0 to 100. So number of nodes can be 0. It means tree can be null. If tree is null, we have to print empty vector, return empty vector, and the node value can be between minus 100 to 100. So let's declare an integer. So here basically we can see that these are all coming in the range of int in C++. So we can use int to store our data, intermediate data. So let's have this vector at answer. If root is equal to null, this is a corner case which we are handling. If root is null, just return the empty vector answer. Now we'll use a helper function for doing the depth first search. So we will call helper, pass the root, the OP, and the level. Level will be initially 0, right? For the root, right? The level at root is 0 as we saw here. Level is 0 at root, then it increases as we go down. So now we'll write the helper function. It will take the first argument, which is a pointer to the root. The second is Our answer vector, it's not OP, I'm sorry. It's vector int answer will pass by reference so that whatever values we change, whatever data we insert in the answer vector, that remains intact, and the same thing we can return here. And this the third parameter is level. Now, if root is null, return 0. Right? If answer dot size is equal to level, return not return. Basically, answer dot push back root val. Then what we are doing here, basically the intuition here is we can see that at any point of time the number of nodes in the answer vector will be equal to level, right? If we have not inserted the rightmost node for that level. For example, at level 0, what is the size of the OP vector initially? Sorry, answer vector. Initially, our answer vector is empty at level 0. So level is equal to 0. Size of answer vector is also equal to 0. At level 0, we insert 1 in our answer vector and move on to the next level. So here level becomes 1 and size also becomes 1, right? Size has become 1. So if that's why we have used this logic here. If answer dot size equal to level, we will insert the current node's value in the output vector. How this logic is helping us, let's see once more. A few more examples. Now we come down and we store 5 in our answer vector. So size becomes 3. Level is also here. Level is what? 0, 1, 2. Okay, level is 2. Then we backtrack and we come here, which is a level 2. We will see, we will see if size is equal to level. No, right? Size is 3, level is 2. That's why we are not inserting this 4 here. That's how this logic is helping us to insert only the rightmost value. Okay. And after that, as we discussed, first we will visit the right child and then the left child. We will increment the level by 1 since we are moving to the next level. Answer will be there, level plus 1, level plus 1. This should work now. Let's quickly run this. This is a problem. Okay, it's a void function. We'll just return here. And this is accepted. Let's submit it. Yeah, we have passed all the test cases. So let's now discuss the time complexity and space complexity. So the time complexity will be at most big O of n, where n is the number of nodes. Why? Because we are doing the depth first traversal, and at max we will visit, not at max, we'll visit all the nodes, right? So time is big O of n, and the space complexity is again big, it is equal to height of the tree, big O of height of the tree, which in the worst case can be big O of n. So space complexity will also be big O of n. How the space complexity is big O of n? Because the space will be required for the recursion stack, right? This is a recursive function, and for the recursion stack, we will need a we will need space of size big O of n. So that's why the space complexity is big O of n. So thank you so much, guys. If you have any doubt, please comment in the comment section. Thanks for watching this.